Today we're going to review notes for Chapter 1. Later on next week we'll have an assessment of sorts. So first of all, before we take off, make sure you kind of split screen between this video and your slide to double check things. So in Chapter 1, when we ask about life science, life scientists work lots of places. So they work in a lab, on a farm, on the ocean floor, in hospitals. They can work in the forests. So the simple answer here is anywhere life exists. So once we started shooting things into space, life scientists could work in space to see what space did to people's bodies. So life science typically happens out in the field, so to speak, where the life lives, or we bring it back into the laboratory where we can control things better. Life scientists study life and anything that affects life. So since pollution can affect life, life scientists can study that. What good things can life science provide? The book really came down on curing diseases or protecting the environment. But one of my favorites is food. Food is awesome. And so life science helps us grow more food. Farmers have more than doubled the amount of food they can grow on the same amount of land, in part due to science and new technology. And so that is a major benefit the book doesn't really highlight. You had to pick a scientist. It didn't really matter which one you picked. So Irene Duhart-Long was in space. Jurat studied shells. Irene Pepperberg studied the intelligence of parrots with famous parrot Alex, who has since passed away. Abdul Lakahani wanted to cure AIDS. They're still after it. They're closer, but they haven't done it yet. Susumi Tonegawa wanted to study inherited diseases. That's my favorite because that's what my eye problem is. And then Dale Miguel wants to study how much space tigers need. Big predators are in trouble because a big predator needs a big home. And wouldn't you know, humans are taking up space. And when humans and big predators come together, the predators lose because humans use their big boomsticks, their guns. All right, so section 2. Thinking life-alike scientists goes into the scientific method. And so we have these ideas. So we see something, we notice something, then we ask a question about how it works. Then we form a hypothesis of what we think the answer is. We test the hypothesis. That's the experiment. We analyze the results. That's fancy speak for doing math. We form a conclusion. We say what we think happened. And if it's worth noting, if our conclusion is we were correct, and if our conclusion is important, we communicate those results to the rest of the scientific community. Now, the scientific method can be more complicated than that. So first of all, you can make an observation, then ask a question. So they left out that step. Form a hypothesis, test it, analyze results, draw conclusions, communicate results. That's all well and good, but you can go another way. But if your conclusion is you messed up, you don't communicate that. So if your conclusion is something went wrong, you either go back and retest the hypothesis and figure out what was wrong in your experiment, or maybe your whole idea was wrong and you form a new idea. So there's a lot of looping back and doing things out of order. There's another way. So science isn't always straightforward. Sometimes you ask a question and form a hypothesis. And when it comes to sleep, we don't need to do an experiment and lock you all in rooms and see how your sleep habits go. No, we can just make observations. So a lot of science can be done just by observing what's already happening and analyzing what already happens. Then you can draw conclusions and communicate results. Science often loops back around because our results often lead to more questions. And that's the best part. So science never really stops. Science keeps going. The more you know, the more questions you have. And science has been growing what we call exponentially because every new discovery brings like 10 new questions that need to be answered. So moving on, how is a prediction different from a hypothesis? A prediction is a possible answer to a question like a hypothesis with an if-then statement. But the important part is the if. The if is an experiment. If we track everybody's sleep, and then the then is what we think will happen. Then I expect females to sleep more than males. So the second part, the then, is a hypothesis. The difference is not all hypotheses can be tested, but predictions must be testable. So to form a prediction, you must have that if statement, the possible experiment. On the self-check in Henry's experiment of jars, he had 3 jars, and the jar that was his control, Henry's testing how soap affects bacteria, is jar C because it has no soap. It doesn't have the variable that he's testing. So you need that there. What if the bacteria grew worst in jar C and they actually grew better with the soap in jar A and B? And soap actually helped them grow. We would never discover this if we didn't have a control. In the same way, with the frog experiment, what if UV light was fewer deformities? What if it actually helped frogs be healthy? We would never know if the students didn't have a fish tank with no UV light for the frogs. So the data for the frogs did support their hypothesis. Almost half of the frogs with 24 days of UV light got deformities, but that is a ridiculous amount of UV light. Also, this doesn't necessarily prove it's the cause of deformities because these results need to be checked by others. In the long run, we found that many factors contribute to issues with frogs, and we can't just pin it on one. It's a combination of parasites, disease, pollution, and UV light. There's all kinds of things going on that together mess up the frogs. Number 8, what causes scientific knowledge to change, or big theories or big ideas? Well, re-examining data and coming to new conclusions. So in the case of several astronomers, they had the same stars as everybody else, but by doing better math, they figured out that the Earth wasn't the center of the universe. Then they figured out that the sun wasn't the center of the universe. Then they figured out that galaxies existed. And so by looking at the same data in a new way, you can come to new conclusions, or most often, by having new observations or discoveries, often with new technology. So for instance, microorganisms couldn't be understood until new technology could prove old conclusions wrong. The idea that the Earth was flat was first proved wrong with math and looking at shadows, and then it was proved significantly wrong by sending rockets with cameras up into space. And as the rocket got higher and higher, you could see the horizon start to curve. So science can change. If new technology or new discoveries or re-examining data proves our old ideas wrong, then scientific theories or what we believe as true need to change. Last up, section 3, the tools of a life scientist. First up, computers. Your iPad is a computer, so it can collect, organize, store, and analyze data. So that's what we're going to do with the sleep lab. We have collected and stored data. We're going to organize it, and then analyze is fancy speak for math. Computers can also graph, which we'll do, communicate, please email me if you got issues, and help with research. Yay, the Google. Computers can do so much more, but they make a lot of parts about science that took a really long time a lot easier. So you'll see that with the math we're going to do in the sleep lab on Tuesday. If you were measuring the mass of a caterpillar, you have 3 metric units to choose from: a kilogram, a gram, and a milligram. The gram is best because they're the right size. So a gram is about the weight of a paperclip, and a big caterpillar might be in the hundreds of grams. It would be less than a gram. It would be like a fraction of a gram, and it would be thousands or tens of thousands of milligrams. It would be like weighing you. We could weigh you in tons, pounds, or ounces. You are just a tiny piece of a ton, and you would be many ounces. Pounds are the appropriate size for you. How tall are you in inches? You had to take your inch height, if you knew it, and then multiply by 2.54 to get centimeters. So that's math. Siri is a great one here. So you can be like, Siri, what's 5'4" in inches? And then you can take that, which is 64 inches, and Siri, how many centimeters is 64 inches? And that works. Or you could actually do the math. The English system of measurement, our system of feet and miles and yards, is based on parts of the human body. So feet were actually based on the English king's feet, and yards were based on how far an arm could stretch. The trouble is, we don't all have the same body, and our measurements wouldn't be the same. The metric system is based on the number 10, and this makes converting units much easier. So I can know immediately that if I'm 170 centimeters tall, that I'm 1.7 meters tall, that I am 0.0017 kilometers tall. But to do the same thing in the English system, to know that I am 70 inches tall, and to turn that into feet, which is like 5.10 something, and then to turn that into miles is ridiculous. And I have to do crazy math to switch units, whereas in the English system, I'm just moving the decimal point around. Temperature and energy. Temperature is the measure of the average energy of the molecules of a substance. All the molecules in a substance are moving constantly, and they aren't all moving at the same rate. So some of them are moving faster, some are slower. And when you average that out and you measure the energy of the millions and billions of molecules in a substance, that's what temperature is. So temperature tells us how much energy something has, but it's not really cold or hot. There is heat, but there is not really cold. And we'll get into that later. There is no such thing as cold. That's not just science voodoo here. All right, well, I hope that helps. And remember, you can play this back and pause the video if you need to add or fix answers.